Today, we are very pleased to be welcoming Emma Woodfield. So Emma completed a PhD in space plasma physics at the University of Leicester in 2002, following which Emma undertook a fellowship at the National Centre for Atmospheric Research in Boulder and has also worked at the University of Liverpool and Lancaster University. In 2012, Emma undertook a position at the British Antarctic Survey, where Emma's research focused on modelling radiation belt dynamics. Emma's work has significantly advanced our understanding of the role of wave-particle interactions in accelerating electrons, specifically in the radiation belts of Saturn and Jupiter, with clear implications for radiation belts throughout our solar system. So I'll hand it over to Emma to present the seminar.
Thank you very much, and thank you for asking me to talk. It's a pleasure. So today I want to take you on a tour of what we know about the radiation belts of the solar system. We've only got half an hour or so, so that's going to be quite a challenge. So the title of my talk is From Van Allen to Juno, Radiation Belts of the Solar System. Here's a rundown of the contents of what I'm going to be talking about this morning. So I'm going to start off with a basic radiation belt dynamics class 101, and then we're going to tour the solar system: Mercury, Earth, Jupiter, Saturn, Uranus, and Neptune. So let's start at the very, very beginning. What is a radiation belt? A radiation belt is a region of energetic charged particles trapped by a stable, mostly dipole magnetic field. Excuse me. The energy of electrons in the Earth's radiation belts is hundreds of keV to a few MeV, enough to damage human tissue and spacecraft electronics. They were discovered following earlier theoretical work by Birkeland and others. The Earth's radiation belts were found in 1958, observed with the Explorer 1 satellite by James Van Allen and his team from the University of Iowa, which is why we often call the Earth's radiation belts the Van Allen belts. Excuse me, sorry. So why do radiation belts exist? Radiation belts result from the interaction of charged particles of the plasma that typically surrounds a planet with the planetary magnetic field. And there are three motion types of this magnetic plasma motion. There's a gyration around the field, there's then a bounce from hemisphere to hemisphere while you continue gyrating, and there's also a drift around the planet with negatively charged electrons going in one direction and positively charged ions going in the other direction. I've also put on this diagram here a variable which we often refer to in radiation belt physics called L shell. And in a dipole, if you assume a dipole magnetic field, the L shell is the measurement from the center of the Earth to the equatorial crossing of the magnetic field line. So this is a picture that probably many people have seen before, the classic donut shape of the Earth's radiation belts with critical satellite infrastructure nestled within it and around the edges of it. Forecasting the hazard level within the belts is a tricky business, and they're not the beautiful static picture you see here. So just a couple of things to note. So there's a low Earth orbit satellite here, GPS satellite here just on the edge of the outer belt, and the two Van Allen probes specifically designed to measure and report on the radiation belts, which was such a success and now sadly not running anymore. So as I said, this is not a static picture. If we move on to a movie, this is a data-based movie. So data from the SunPex satellite was used to model the whole radiation belt. And these are from the Halloween storms in 2003. And this movie covers almost 2 months worth of data. But you can see that the radiation belts at the Earth are very, very dynamic. They spread out, they get more intense, new belts form in the inner edges. It's a very dynamic picture. And why are those belts so variable? They're embedded in a variable magnetosphere, of course. We're affected by the solar wind and mechanisms from inside. But there are also many sources and losses of radiation belt particles, and they vary and interact to fuel this highly dynamic environment. So let's get to the basics of what runs a radiation belt. So let's start with the sources. We have the classical radial diffusion, which is the long-standing theory behind how charged particles are energized to the relativistic energies of radiation belts. And this is basically, you have asymmetries in the electromagnetic field that a charged particle will see on its drift around a planet. And those asymmetries lead to a diffusion in the direction of the phase space density gradient. And conservation of the first adiabatic invariant, that's a conservation parameter associated with the particle gyration. Conservation of that results in an energy increase of the particles as they move towards the planet. Or conversely, if they're moving away, if the gradient is sending them in the other direction, then they will lose energy. But typically we think of this as energizing particles moving towards the planet. Then we have synchrotron resonant wave particle interactions. So circularly polarized waves interact with gyrating particles. They're both moving in a circular sense. And then when they match at the right frequency, then they can exchange energy between them. So on this slide, the sources slide, we're talking about accelerating charged particles to higher energy. An example of this is Whistler mode chorus waves at the Earth, which are well known for accelerating electrons to higher energies. Okay, and then we've got cosmic ray albedo neutron decay, often called crammed. So we have incredibly energetic cosmic ray particles, protons, barreling into the Earth's atmosphere, or atmosphere of any planet, colliding with the molecules and constituents of the atmosphere there. And quite often that will result in the production of a free neutron. Neutrons do not like to be free, and they will decay within the space of about 15 minutes, leaving a proton, an electron, and an anti-neutrino. So what we end up here is something that there was a neutral particle happily going about its business within the atmosphere, which then via this process becomes charged particles, which then become trapped in the magnetic field. So we go from a neutral constituent that isn't affected by the magnetic field to charged particles that then are. So that's crammed. Then we have charge exchange. So that's a similar sort of idea to crammed in some respects, in that you've got collisions of particles, one charged, one not, and then you can exchange the charge between them, so that then the constituent that's trapped changes. So it might have a high energy. You might move to having a higher energy charged particle where previously you had a high energy not charged particle, for example. And then finally, a relatively new one that's only been discovered in the last, or the importance of which has only been discovered in the last couple of years, which is rapid adiabatic transport. Typically, we'd call this convection, but there are certain circumstances, certain planets where this is a really important process. At the Earth, it's not really important. It only really affects the lower energy electrons. But at Saturn, as we'll get to later, this is a really important process. So that's the sources. Let's go on to the losses. Okay, so you've got your wonderful, highly energetic, relativistic, let's say electrons, but also ions. How might we get rid of them from the radiation belts? So obviously, if you've got physical objects to crash into, such as moons and rings, large dust particles, then you're going to lose some particles from your radiation belt. So that's the moons and the rings and dust part of that. So there's a fairly basic high energy, slams into a large rock. But the details are important, though, is that the drift speed around the planet and the radius of the particle gyration have important effects on how much you actually lose. If you're gyrating around a magnetic field and it actually happens to be larger than the moon, then you're not necessarily going to hit it, for example. Then we have so I've put the magnetopause in here. So if the drift path, the magnetic drift path on which your charged particle is moving encounters the edge of the magnetosphere, the magnetopause, then the particles can't remain trapped. There's no closed drift path for them to sit on, and so they are lost from the radiation belt. And this wouldn't be too much of a problem if everything was static, but obviously the magnetosphere expands and contracts with the pressure driving from the solar wind, for example. And so the magnetopause moving about and changing your trapped drift orbits is an important process of loss for the radiation belts. Then we've also got smaller collisions, so not moons, but neutral particles, typically in planetary atmospheres, or from some of the moons in the solar system, they actually give off neutral particles, and they have what's known as neutral tori. And so then we have other smaller collisions. So charged particles, if their bounce motion takes them deep enough into the planet's atmosphere, they'll suffer multiple collisions with the atmosphere and not bounce back out again. So you will lose those particles from the radiation belt. And then, so that's that sort of atmospheric effect. If we're talking about output from a moon, which is a more sort of tenuous neutral environment outside, quite well outside of the planet, that just tends to reduce energy and maybe change the direction of the particle. But they don't tend to be lost in those circumstances. The main loss there is to the atmosphere. Then we have synchrotron. So synchrotron radiation isn't an important effect except at Jupiter, where it is an extremely important effect. So synchrotron radiation, very, very ultra-relativistic electrons gyrating, circulating very, very fast around a magnetic field, give off synchrotron radiation, electromagnetic radiation. Just they're spiraling too fast, they've got to shift some energy somehow. And so that is a rapid energy loss mechanism. It's also a very directional loss mechanism because you lose perpendicular velocity, which means that actually your particles will go further up the field line in their bounce trajectory because their velocity direction is now more parallel to the magnetic field line than it was. So not only do you lose a lot of energy quite rapidly, you also change the direction and head those particles up towards the atmosphere, where you may well lose them. Then we put the wave particle interactions back in again, so that can go either way. You can either pump up the waves using the particle energy, or you can pump up the particles using the wave energy. So if you're going to lose energy from the particles, put it into the waves, you're going to reduce the energy and change the direction again of your charged particle motion. And that also typically tends to send the particle higher up towards the atmosphere along its bounce path. That bounce path gets closer to the atmosphere, and then you tend to lose particles through that mechanism. And then also you get charge exchange again, just as you could you could have a collision where your energy increases. You've got a neutral particle that's very energetic, you could gain charge. You could also lose it, and then you could lose it from the energy levels that we consider to be part of the radiation belt. So there's an awful lot of processes going on here, many of which we don't have to worry about the Earth. But at the planets, the other planets, then a lot of these really come into be very important. So solar system planets we know have trapped particles. So I've got Mercury, Earth, Jupiter, Saturn, Uranus, and Neptune. So that's quite a lot actually, but basically you have to have an intrinsic magnetic field. It has to be strong. it has to be mostly dipolar, so it has that bar magnet picture of the magnetic field lines, so that you can actually get trapping using those three motions of gyration, bounce, and drift. And all these planetary objects do meet those criteria. So let's start with Mercury. Okay, so Mercury is a bit of a strange one. It could be a should we count it or not really. It does have trapped ions and electrons, but they're very low energy. It has an intrinsic, mostly dipole magnetic field. This is one of the criteria we need to have a radiation belt. But it's a very weak magnetic field, and the magnetosphere is very small, which means that the radius of the charged particles gyration is very important. So if you've got a very energetic particle, which will have a larger radius of gyration, then the chances are it can't be trapped, because it'll either hit the planet itself, or be lost to the magnetopause, which is very close in. So it's very easy to lose energetic particles. Nonetheless, it does have trapped lower energy particles, but they're also quite variable in their trapping. They tend to only be trapped when the solar wind is quiet and low pressure, and then you've got a decent sized magnetosphere. So that's sort of we call it, we say it has transient radiation belts, but it's really very, very low energy in terms of what we normally call a radiation belt. So just a quick tour of Mercury and move on to some of the bigger planets. So Saturn. The magnetosphere of Saturn has some particularly important features when considering the radiation belts. Firstly, the magnetic field is upside down. The poles are reversed, north and south are reversed compared to the orientation at the Earth. And that has some very important effects on the drifts, which we'll come to later. Saturn's magnetosphere also has a significant plasma input from the moon Enceladus. These are water group ions emitted from in like geyser-like form from Enceladus, which is about 4 Saturn radii, and they form one of these neutral torus formations of particles within the magnetosphere, and that also leads to extra plasma when some of that neutral is ionized. We also have the plasma strongly co-rotating with the planet for quite some distance, so that also comes in important later on. And it also has a big chunky set of rings, which are the biggest and most absorbing set of rings in the solar system, and that wipe out a big chunk of the radiation belts at Saturn. Thanks to the Cassini-Huygens mission, we have a really nice data set of what's been going on at Saturn, and actually it's in the end is the planet that I've worked on most. So the belts of Saturn are quite different. So we have a set of proton radiation belts and an electron radiation belt. The proton radiation belts have significant gaps carved out by the moon orbits, creating individual belts in between the orbits of those moons. The energetic electrons are not so affected by the moons, and you get a more continuous belt without those gaps where the moons are. And that's all down to how fast the moons move in relation to the drift of the particles. So we've got here, so Enceladus is the moon with the geysers that's giving off all the lovely water ions, gives you a nice gap there. And the strong proton belts only go out to the orbit of Tethys, which is at about 5 Saturn radii. And very recently discovered, thanks to the grand finale part of the Cassini mission, is a new set of proton radiation belts we didn't know about before, right in next to the planet, inside of the rings. So you can see that the main rings just obliterate the radiation belts. Nothing can bounce and survive through the main rings. But inside of that, then you have a proton radiation belt. And this is thought to be mainly derived from the Crand process. So those galactic cosmic rays coming in, hitting atmospheric neutral particles, generating those free neutrons, which then decay and leave you a proton radiation belt. So they should also leave behind some electrons as well. But the observations are that you don't see electron radiation belts in this region. The CRAN process only tends to produce relatively low energy electrons of a few hundred keV. And there are also Whistler mode waves present in this region. And so there is quite a decent chance that the electrons actually just get scattered into the atmosphere. So we see a proton radiation belt in here, but not an electron one. The electron belts stretch from the outside of the main rings at about 2.3 Saturn radii out quite a long way. And you'll get little dips occasionally from some of the moons, but it's basically continuous. So I've tried to summarize where the processes are most important at Saturn. So this is, here we've got the proton belts I've put in blue. So there's the one inside of the rings there, and then you've got the protons with the gaps in between. So most of the proton belts are contained within this region here. We also have the electron belt, which sort of starts just outside the main ring and then continues outwards quite a long way, but losing intensity as it goes. We also have these things called electron microbelts, which are just inside here, which is where the F ring is, which is one of the weaker rings at Saturn. And that's formed by quite a peculiar mechanism that I'll talk about in a little while. Basically something called banana orbits. I'll get to that in a minute. So we have the main suspects of processes here. We've got the radial diffusion. Is expected to radially diffuse particles inwards. It's a very slow process at Saturn though, much slower than it is at the Earth. So we're talking years really to transport particles by radial diffusion. Then we've got the local acceleration from wave-particle interactions. So the waves we're talking about here are Z-mode waves, chorus and hiss. Unusually hiss. Hiss is normally thought of as a scattering loss mechanism at the Earth, but because of the different plasma regime at Saturn, the hiss actually causes some acceleration as well. So the waves are active in different locations in here, but there's acceleration from one wave or another somewhere across this region. We also have various sorts of injections at Saturn. So we have dipolarization injections, not quite substorm injections, but a similar sort of idea. We have a dipolarization process going on. Then you also have interchange injections of tens of keV electrons, which are to do with fingers of denser plasma going outwards and being replaced by warmer, less dense plasma coming in. And those are interchange injections. And then we've got this new process, the noon. So there's a noon midnight electric field at Saturn, approximately noon midnight. It's a bit off that axis. And that electric field produces a rapid transport, which I'll talk about in more detail in a moment. And that's a very newly discovered mechanism for shifting electrons really rather quickly at Saturn. Then we've got some loss processes. So we've got the neutral torus that comes from Enceladus, and associated with those, the ions that come off from the moon as well. Then you get some ion cyclotron waves, EMIC, and those will cause scattering losses from the radiation belts. You've got the E ring that covers this sort of region here, which is a much more tenuous ring, has more of a not a very substantial effect on the radiation belts. And then you've also got some more neutral torus from Titan further out. So let's go back to these electron microbelts and talk about electron drifts at Saturn. So as I said earlier, the electron drifts the magnetic field is upside down at Saturn. So as a result of that, your electrons drift in the opposite direction to what they would do at the Earth, but the rotation of the planet is still in the same sense. So what you end up with is an an electron magnetic drift due to the gradients and curvatures in the magnetic field opposing the plasma co-rotation driven by the planet's rotation. So the plasma co-rotation at Saturn's really strong and goes out to quite a distance, and that opposes the electron drift. So there is a set of circumstances at the right energy where you can have an electron that does not drift. It stagnates and doesn't go in either direction because the co-rotation and the magnetic drifts are offsetting each other. So that is where the electric field, that approximately noon midnight electric field, takes over and then transports the particles in. So that field is variable, and that variability causes some really rapid transport. The other important thing is when that stagnation happens, you can't apply radial diffusion. Radial diffusion requires a drift around the planet to work. And if you're not drifting around the planet, you're not going to radially diffuse. So this electric field really takes over at that point. And the result of that is that you get these zebra stripes. So over here, we've got some measured flux from the Cassini spacecraft. The top plot shows energy in keV versus time along the bottom. There's a line in here, which you can just about see, which says CDR on it. That's co-rotation drift resonance, which is another term for this stagnated energy where the drift doesn't go in either direction. Okay, and so if you then sort of isolate this, you can see the stripes in there fairly clearly. You can then isolate those stripes more clearly by a little bit of magic processing. And if you then plot that, instead of against energy, if you plot it against the drift frequency versus time, you can see that there's the drift frequency stagnates at the 0 point, obviously. So that's your stagnation frequency. You can see that the zebra stripes are all above that frequency. Now, if you go ahead and simulate this situation as Howard et al. Did in 2020, you can really clearly reproduce these zebra stripes. So this is the energy plot here with the co-rotation drift resonance line in there, and this is it replotted as drift frequency against L shell in this case. And these are the kind of orbits that are producing these signatures. So here is the famous banana orbit. So these are dependent on energy. You can see here, so the 860 keV in this case, so this is a backwards tracing. So you've ended up at this cross point here and you've come around this orbit to get there. So you are not drifting around the planet. This is the planet here. You're doing this peculiar little orbit just off to one side. And those are energy dependent. And you might think that the effect of this stagnation energy would be limited pretty much to spot on that energy, but actually the effect from the observations has been found to spread to 2 or 3 times that energy in both above and below the stagnation energy. And the results of this, so you can move multiple L shells in just a few days, which is a fun, really fast way of moving particles about. And it really makes modeling of radiation belts at Saturn quite hard because you can't use radial diffusion anymore. And so these banana orbits are what are thought to create these little micro belts. So they're not all the way around. They're not a symmetrical and local time effect, the micro belts, but they are observed in specific places in local time. At around about 2.3 Saturn radar, where the F ring is, and they're thought to be due to these little trapped orbits. Okay, let's move on to Jupiter because time is moving on. So Jupiter's the giant of the solar system in every respect, and that also applies to the radiation belt. Here's a picture of the magnetosphere and a picture of Juno, which is still orbiting there and has a really nice extended mission coming up. So it's similar in some respects to the Saturn magnetosphere. You've got a plasma torus and a neutral torus, but this time it's from Io, not Enceladus. And Io is volcanic, so it's not not water particles this time, but it's sulfur and oxygen driving that torus. The magnetopause is a very, very long way out. So the radiation belts that we think about are really in this region in here, in the mostly dipolar region of the magnetic field. So Juno, there's some very careful orbit planning put into Juno to make sure that Juno doesn't go through the most intense parts of Jupiter's radiation belts. Very, very little data has been taken in the most intense parts of Jupiter's radiation belts, which is entirely understandable, but a bit of a shame. And maybe one day we'll be brave enough to send a satellite really into the harshest environment in the radiation belts of the solar system. So Juno skirts across the outside of the top and then sort of underneath as it goes very, very close to the planet and then out again. So we get a little tiny bit of information just from the horns of the radiation belt here, as they're called, and more information about general waves and things that might contribute to the radiation belts from further out. This is a plot of the intensity of various particles as you go out an L shell. So we've got some electrons in the black and blue, and getting quite energetic electrons in the light blue and the green. So this is 31 MeV electrons here in the green. So that's already some pretty hefty electrons observed even at 10 RJ Jupiter radii. And then the yellow line, which is a bit faint here, is protons, energetic protons, and then you've got oxygen. So you've got an oxygen radiation belt as well there in red. And as I said, inside of Io here, we don't have an awful lot of data in here because nobody wants to go there. So this is a really quite intriguing region, and there are hopefully some similarities to what we saw at Saturn with the grand finale orbits, which covered this sort of region in a similar-ish sort of environment. So we hope to make some extrapolations from those observations. So we can't get there in situ directly, but we can look at it remotely. So the very most intense parts of Jupiter's radiation belts, where the electrons are in excess of 50 MeV up to even 100 MeV, you can see them in the synchrotron radiation, and you can observe the synchrotron radiation either using radio telescopes from the Earth, or this data here shows this was actually taken by Cassini as it went past Jupiter on its way out to Saturn. So that having this really, really intense set of electrons quite close to the planet, so this is out to about 4 Jupiter radii over about here. If you're going to get up to energies of 50 MeV to 100 MeV, then you need, if you're going to do it by radial diffusion, a source of a few hundred kiloelectron volts to a few mega electron volts somewhere near 10 Jupiter radii. So let's have a little look at that sort of region. So radial diffusion has been around for decades, but it's only more recently that we've come to understand the importance of local acceleration through wave processes at Jupiter. Just as it's become an important process at the Earth, it's also important at Jupiter. And if we look at, so this is the Galileo data reprocessed at Jupiter from an L shell. So this is L shell of 10 out to 100. And it's been given this theoretical format. So this is a sort of power law type dependence. So there's an exponent here, gamma, which is what's plotted over here on the y-axis. So dependent on the energy, that this is the base flux J naught of the particles, the energy electrons, and then you've got a critical energy in here where the spectrum takes a turn downwards, and you start to lose, that the intensity goes down sharply, and so that happens at this critical energy, and then you have this factor KT, which tells you how sharp that changes. And so Peter Coleman went and fitted spectra to all the Galileo data to measure these variables, and that's what we've got plotted here, the gamma, this exponent up here. And then you can do you can work out what the adiabatic heating from a radial diffusion point of view. So that's you're conserving the first adiabatic invariant, and that heats the particles. And if you follow that theory, then you should get a line that follows this orange line here. And for the vast majority of Jupiter's outer magnetosphere, then you do tend to follow that line. So the data's obviously in black, and then you've got a median fitted in the colours here. But once you get inside around about 20 Jupiter radii, an L shell of 20 on the equator, then things start to go really haywire. And so there's definitely something different going on inside about 20 Jupiter radii. So coincidentally, that's where the Whistler mode chorus waves are also, that's where they're at their strongest, where they're at their most intense. So this is a plot of wave intensity versus distance at Jupiter. So we've got Io in here, heading out to about 20 RJ out here somewhere. And so there's a peak somewhere between Io and Europa is where the intensity peaks. And we did some modelling back in 2014 to try and work out what effect those chorus waves might have on the electron population there. So we used, so Jupiter also has injections, and those injections have been observed to occur approximately every 3 days, very approximately. So we used that as an input to our radiation belt modelling, using the waves as a driving force. And we found that actually the injection comes in, the waves grab those electrons, which are about 10 keV, and accelerate them up to about an MeV or thereabouts, a few MeV. And then those electrons stay trapped in that sort of MeV population region. And so you get a bunch of injections that get accelerated by the waves, you get another bunch of injections that get accelerated, and so on. And so you get this cumulative process whereby you build up a radiation belt and an energy of about 1 MeV at around about 10 RJ over here, which is coincidentally where we need that seed population to be taken by the radial diffusion, then to be taken to those extremely high energies very close to the planet. And so this is this combined with the previous plot where we show that the adiabatic heating by radial diffusion tends to not really work as a theory inside about 20 RJ, then this wave particle interaction with chorus wave could well be part of that deviation from the ideal of radial diffusion. So that's acceleration by waves. We also have wave losses at Jupiter. So if we look at the proton belt, so this is greater than 15 MeV protons at Jupiter, modelled using the French Salambo code by Quentin Lennon. If you don't use any ion cyclotron waves in your proton model, then you find it hard to match the data from the spacecraft passes that we have. And there are ion cyclotron waves around Io, so you get pickup ion process, which produces the instability, which gives you the ion cyclotron waves. The ion cyclotron waves then interact with the proton and cause losses. And if you include that in the model, as Quentin did, then you much better match the passes from the spacecraft. So here we've got an L shell along the bottom here, and they've got integral flux up the side, and we've got the Galileo data is in blue. And then you've got the Salambo results without using the ion cyclotron waves in purple. And then with using the ion cyclotron waves, you get a much better fit to the Galileo observations of the particle flux. So the wave losses are also an important process. Then a very recent discovery is a new inner ion belt at Jupiter. So we had a new proton belt at Saturn inside the main rings. And at Jupiter, we've got a very close to the planet ion belt that was discovered using the Juno data. So it lurks very, very close into the planet in here. And here you can see some data from Juno showing the protons and the oxygen with the different log of the differential intensity in color here. And so M shell, when you're talking about a dipole equivalent, is the equivalent of an L shell. And you can see there's an ion belt out here, and then it all goes quiet for a little bit. Here's IO, and then you're going inside of IO, and then there's this very strong burst very, very close to the planet. It doesn't necessarily go all the way around because of the close to the planet, the magnetic field it has the great north blue spot, as it's sometimes called. The field is not smooth and dipole, and so there are bumps and wiggles, and that means you can't trap the ions all the way around in local time. So yeah, another new ion belt. So let's move on to Uranus and Neptune. Now, we haven't got an awful lot of data from Uranus and Neptune. We've got one pass from Voyager 2 at each planet, but they are really, really fascinating places. If you look at the magnetic field and rotation setup of Uranus and Neptune, they're very different to what we're used to at Earth, Saturn and Jupiter. So Earth, Saturn and Jupiter, you've got your rotation axis and your dipole axis are relatively close together, very close together in the case of Saturn. Okay, the field might be upside down for Saturn and Jupiter, but you've got this essentially sort of more or less lined rotation and magnetic field setup. When it comes to Uranus, you've got a rotation axis that's tilted by 90 odd degrees in a very, very peculiar orientation, and then on top of that, you've got an offset of the magnetic dipole of nearly 60 degrees, which is really, really large and leads to some very, very interesting setups in the magnetosphere. And also Neptune has a very, very large offset from the rotation equator to the magnetic, rotation axis to the magnetic axis. And you also have a significant offset of the center of the dipole part of the field. So two very, very interesting setups from a magnetosphere point of view. So we've had Voyager 2 data. So these are diagrams of the magnetosphere as it would have been in 1986 when Voyager 2 flew past the planets. So obviously, Uranus has an 84-year orbit. The seasons are very, very long, but it also has a 17 and a bit hour rotation. So what happens is you've got your rotation axis in here with your magnetic field going in one direction. As over those 17 hours, that magnetic field rotates around to will give you a very, very rapidly changing magnetospheric setup in its interaction with the solar wind. And that spin period and large offset leads to a helical magnetotail. So these are magnetic field lines here. So this is a fairly typical setup for an Earth magnetosphere, but this massive offset of the dipole tilt and the rapid rotation at Uranus gives you this weird twisted magnetotail structure, which is, it's hard to believe that you could find a radiation belt that would stay stable within this setup, but you can, and Voyager observed it. So let's have a look at those observations. So on the left, we've got the more energetic electrons as line plots, and then you've got colors of the electrons and protons. These are lower energy, so that's 1 MeV in the protons and 1 MeV in the electrons. And then you've got a greater than 1 MeV line here, greater than 3 MeV, and greater than 7.6 MeV. Time along both axes at the bottom. And you can see there's a very nice set of radiation belts here, nicely sort of delineated by the moons. So you can see these dips here where the moons are important in taking out some of those electrons. And for comparison here, they've put the Saturn, the equivalent Saturn measurements from Voyager underneath. And you can see it's much smoother. The moon effect of Saturn is really not there. But at Uranus, the moons have an effect because the electron drifts will impact on the moons more. So we've got a really strong, stable, well, presumably stable. We only have one inbound and one outbound past, but to reach these levels of flux, it has to have been there for a significant amount of time. And they're sort of constrained by the orbit here of Titania, just inside of 20 Uranian radii. And as you go up in energy, the constraints get smaller and smaller. So the very highest energies are only in quite close to the planet. But yeah, a strong and must be stable radiation belt, because it wouldn't get to those levels without having been there for a very long time, despite all that crazy magnetotail action going on. Inside that, there's a dipole region that's staying steady enough to sustain a radiation belt. And then finally, Neptune. So a few years later, 1989, Voyager 2 flew past Neptune, and the path that Voyager 2 took past Neptune went extremely close to the planet, within 0.2 Neptune radii. So we've got a quite different view of what's going on in here. So a very similar set of plots to the previous ones from the Voyager data. We've got multiple MeV electrons here, protons and electrons up to around an MeV here. Quite symmetrical looking belts, pretty much constrained by the orbit of Triton, which is that strange retrograde moon that Neptune has. And so the radiation belts only seem to go out to the orbit of Triton. But again, they're not as strong as they are at Uranus. And in fact, in the lead up to the Voyager pass of Neptune, they're expecting something much more powerful, but actually that's not what we see. So that's quite interesting. There's lots of little blips in here which may not actually be due to moons, because the pass is so close to the planet. We've got atmosphere effects and also drift shell issues where the magnetic field is not beautifully dipole, that the drifts may not complete all the way around the planet. So these are not necessarily moon signatures in here. So some beautiful MHD simulations of Neptune's mass density done by Mesnetson in 2016, which just kind of brings home Voyager's pass through this rapidly rotating system. So Neptune has a point where it's sort of an Earth-like configuration, and then further around in its sort of rotation of 15-ish hours, I can't remember exactly, it'll actually be pole on to the solar wind, which is this configuration here. But the Voyager started in this configuration, and then a little bit further in its path, it sees it in this configuration, and then it moves back to this configuration. And so you've got this rapidly rotating system. It's really intriguing that you can have this stable region of trapped radiation within inside that. So the future. The radiation belts of the solar system are incredibly varied, much more so than I suspect we ever imagined they would be. And we are actually still discovering new mechanisms that sustain them. The convection at Saturn was only discovered a couple of years ago. And we've learned an enormous amount from the long-term observations made by Cassini at Saturn and Galileo and now Juno at Jupiter. There are some really critical holes in our observations though, and that's the harshest region at Jupiter, where there's extremely little in situ data, and also just the one pass of Uranus and Neptune. So we really need some BRAVE to go in those harsh regions, and long-term future missions to measure high energy electrons and ions to fill in those gaps. Thank you for listening.
Thank you. That was really interesting, and a really nice, clear overview of all of those very different regimes. So if anyone has any questions, please type them into the chat, or use the hands up function if you would like to ask it directly. We already had one come in, which kind of follows on from your last slide. So Diran Kataria asks, is there scope or possibility to change the Juno orbit so that Juno does go through the intense part of the radiation belt towards the end of mission, perhaps?
I know there was some talk about that, and the orbit will be changing as part of the extended mission. They're bringing the orbital period down to more how it was originally supposed to be, moving into new bits we haven't been to before. So I'm kind of hoping they might take at least a dive like Cassini did at the end, and see what we get from that, which would be amazing. One more set of data.
That would be good. You mentioned at Jupiter, sorry, this is just my follow-on question. You mentioned at Jupiter that you can understand the radiation belts using the synchrotron radiation. Mm-hmm. Has there been any like conjunctions where you can use both synchrotron and Juno passing through the horns of the radiation belts? And has that added like any, because that sounds like it could be quite interesting.
Yeah, I'm not sure actually if they've done any ground-based radio telescope observations when Juno's going through. I'd like to hope somebody would be. But Juno also has, so the microwave radiometer on Juno measures the right frequencies for the synchrotron. So their aim is obviously to look under the cloud tops. So the synchrotron is their noise. So they can also see some of this. So hopefully there is some data out there, but I haven't actually looked at it myself. Yeah.
Okay, thank you. That's quite interesting. We have another question from Timothy David, who asks, what could be responsible for Venus and Mars not having a radiation belt?
So Venus and Mars don't have an intrinsic strong magnetic field driven from within inside the planet. So Mars, for example, has got crustal fields that just aren't big enough or strong enough to trap energetic particles, basically. So yeah, you need a good, strong, internally driven magnetic field. So Mercury's on the edge of what you could possibly have, basically.
Thank you. If anyone else has a question, type it in now. We've got 5 minutes left. If not, I made quite a few notes, so I might just ask my own questions. So one of the things which I thought was quite interesting about Uranus and Neptune was that they have, if I understand correctly, this offset dipole. So from just me not knowing anything about them until you told me, it looks like there could be quite a lot of loss due to collisions with the atmosphere, because you have at one hemisphere quite weak magnetic field. So the particles can reach deep into the atmosphere.
Yeah.
Would that be true? And would that make it a bit more difficult for them to sustain the radiation belts? Like, what are the implications of that?
To be honest, I don't really know. The observations are fairly symmetrical. So I think in fact, they just surprise me in their strength, and that that's there and obvious. So they've clearly overcome problems like that. But I think my major worry is actually what happens on the outside edge of that sort of stable dipole region. Despite all the shenanigans that's going on further out and all the twisty turny stuff, I think inside the atmosphere reaction is probably similar to what we get at Jupiter, maybe. And it's so hard to tell with so little data. But yeah, and clearly whatever atmospheric collisions are going on, they are overcome because it is sustained. There are also wave observations at Uranus and Neptune. So we've got Chorus and His. There's even some Z-mode wave observations at Neptune. So there's probably going to be some local acceleration processes going on there too. Yeah, it's a really fascinating region, but I'm coming to think of it as this sort of encased, safe little region inside all this big mess of twirly stuff that actually can sustain these belts. And why Neptune is weaker? Maybe it could be the reason that Neptune's weaker than people think it ought to have been. Because it's coming up to go to the Voyager flyby of Neptune, they really thought it was going to be really good, strong radiation. And oh, it's not quite as strong as we thought it was. So yeah.
Yeah, perhaps all of that wave activity just overwhelmed any like increased atmospheric loss?
Yeah, I'd really like to get my model up and running for Uranus and Neptune, see what we could do.
And that tail configuration just like blew my mind. I hadn't seen
it.
It's
crazy, isn't it?
Yeah. Yeah. So would there be lots of, sorry, I'm just asking follow-on questions because no one's interrupting me. Would there be like lots of reconnection processes and things like that happening in that tail or that twist?
Yeah, so the reconnection opens daily, twice daily, I can't remember. But yeah, basically you get multiple reconnection options per day. Yeah, so that's, the sort of more, the wider magnetospheric processes are also incredibly interesting.
Yeah, loads of plasmoids everywhere. Unless I'm missing it, there's no more questions coming in, so I just have one more and then I'll stop. I know at Earth we have a really variable magnetopause location, so you can get these like huge dropouts in the radiation belts. Is that important for the radiation belts of Saturn and Jupiter, or do they exist like quite far away from the magnetopause?
Jupiter, certainly. The radiation belt of Jupiter is a very long way away from the magnetopause, so that's not really an issue at Jupiter. At Saturn, it's a bit closer, but even then, Saturn magnetopause is typically 20 odd Saturn radii off at the nose, and we've really only looked at sort of up to 10 Saturn radii, so we're still well within that region. So yeah, magnetopause shadowing is really not an issue for Jupiter and Saturn. We've got plenty of other issues, and it's really finding the balance of which sources and losses are important at different planets to try and balance everything out, find out how they work.
So because you don't have the magnetopause being so much of an issue, does that mean you don't see like these very rapid dropouts? It's much more sort of like slowly varying.
Yeah, and so we do get time variability, particularly at Saturn, but that's more to do with this radial transport process to do with the convection, where you get chunks of flux moving several L shell in a matter of days. So it's more of a motion inwards rather than a chopping off at the edge kind of scenario. Jupiter, we're not quite so sure about the time variability at Jupiter. Hopefully we get some more data on that from Juno, maybe somehow.
Yeah, I guess it depends how regularly like Juno passes through. So what is its orbit's length? Like how often does it pass?
Juno sort of dips in and out of the magnetotail as it goes along, because of so Jupiter's dipole axis is offset by about 10 degrees from the rotation, so you get this sort of wiggly path through the magnetosphere. And so we're starting to see some of the wave populations and particles in the outer regions of the radiation belts. So that's proving to be quite interesting to work on. It's just that really inner bit that we haven't really looked at. But yeah, you can actually get quite a lot of information from the outer parts of the Juno orbit.
Okay, that's really interesting. We've actually gone over time because I was asking too many questions. But thank you so much, Emma, and thank you everyone for attending. That's it for today. So we will have our next online seminar next month, and I'll circulate information about that via the usual channel, so the missed mailing list. So yeah, enjoy the rest of your day, everyone. Thanks again, Emma, for a really interesting seminar. Goodbye.
Thanks very much.
Thank you.
Thanks, Emma.